I don't really have anything planned, so this is kind of filler content. It would just really be me messing around. I'm looking into conic sections. I'm not really making any progress. I'm gonna ask about this in the end. Right now, I just wanna show you my crack at the Collatz conjecture. And if you don't know what that is, basically, you insert a seed number. Let's call that number n, and you multiply it by 3, then add by 1 if it's odd, then divide by 2 if it's even. Divide it by 2 if it's even. And you repeat this process till you get to a loop, or see if it grows infinitely. Who knows? But the conjecture states that it will always reduce to 1. And it'll get into a loop with between 1 and 4. Okay, so my attempt at solving the problem involved not looking at it from inserting numbers and checking, but generating numbers that will always reduce to 1. So for example, let's say we got the first generation. I like to call it generation 0, and that's equal to 1. 1 will always reduce to 1 because it's 1. And then the next generation, which is generation 1, you take generation 0, multiply that by 2 to the n. That gives you an infinite list of numbers. And then you fit those numbers. Let's call this n1. We subtract by 1 and then divide by 3. Now an interesting note is that 4 to the n minus 1 will always be divisible by 3. There's a proof for this. I don't want to get into it right now, but it's an interesting proof. I think it's used as an introduction to proof by induction. Anyways, now you have an infinite list of numbers between 1 and 0. Okay, after that, the next generation, you do the same thing. G2 equals the previous generation times 2 to the n. Put that in n1 minus 1 over 3 over 3. If you notice something, that when n equals 0, you get the original list of G1. So the next generation will always include all the numbers in the previous generation. Now it looks something, if I'm going to generalize this, it would look like I already used n right here. Let's just call it uppercase n equals g n minus 1, multiply that by 2n. I don't know how I would do this in formal notation. I don't really know a lot of math notation. Okay. I would know that this is kind of union, but anyway, it doesn't matter. There are two ways you could prove that all of this will eventually lead to every number if you conduct this process infinitely. One of them I think would be impossible, which I'm gonna discuss that one first, which would basically asks you to prove that it will reach every single number through that has prime factorization with every single possible combination with each n, which I think would be impossible. Firstly, because it involves primes, and a lot of the problems that involve finding predictability with primes are usually impossible to solve, or at least really hard to solve, like the Collatz conjecture, which states that every even number is a sum of two primes, can be described as a sum of two primes. But that's getting off topic. The point is, primes are really random, and it's really hard or impossible to find any order in them. The next one, which I think has more promise, is what you take, let's say, a gap between 2 to the 4 and 2 to the 5, and the conjecture is that for every gap, between every power of 2, there is a finite number of generations that will cover every single integer between those two numbers, or maybe an infinite, who knows. But so long as you can establish a rule and prove that n amount of generations will cover every single number, like you could say it takes 3 to the n, with n being that amount of generations will fill all the numbers here. It doesn't matter. Just so long as you could establish a rule and prove that rule, you could prove that every single number is covered. Or you could always say that, you could say something like, between every single one of these, you could always say that, oh, at some point you will always have one more number that fits between these two, or these two, and so on. So I guess I think that one has a lot more promise. I don't know if it's been tried before. The only video I've seen on this problem is the one by Veritasium. I don't know how you pronounce that. I thought this problem was really cool. But anyways, here's the thing I want to make a video on, but I can't because first of all it's too hard, and second of all I just don't know how to. I just don't really have time. So it involves conic sections. We still haven't really reached conic sections, but basically you take like two cones and put them in like a 3D coordinate system like that, like their tips on top of each other, so it makes this like hourglass figure. And then you have a general function. It's a times x squared. It's gonna take forever. Plus b times xy, x times y, plus cy squared, plus dx plus ey plus f equals 0. Let me finish writing this. What I want to find out is if you can insert all of the 6 numbers into a function and get a plane, get 3 points of a plane, which would be the origin, the y-axis, first unit of the y-axis, and the first unit of the x-axis. Let me just give an example real quick. So a parabola would be like a equals -1 and e equals 1, because it would be y minus x squared, and f would equal 0. Y minus x squared equals 0. That gives you y equals x squared. And you get a parabola. Now a parabola would basically be a plane. It's had like a 45-degree angle, so that this goes on forever, but this never touches anything down here. There's also circles, which you could have like y squared plus x squared equals 1, and then you have a plane that crosses right here, and that gives you the unit circle. And you can also have you could also have hyperbolas, which is y squared minus x squared or x squared minus y squared. I don't know how they do, but basically you have a plane that crosses like that, so that it hits both the top and bottom cones. And if it's 0, it gives you this. It intersects it perfectly, where it touches that point, and it just gives you these two lines. If it's something other than 0, let's say like 2, you get something like this. I don't know what it's like in that case, or it would be something like this. Now what I want to figure out is if you can, again, input all these values into a function, maybe a matrix of some sort, and get back these 3 points: the origin, the unit x-axis, and then the unit y-axis. If you could like send me a video that does this, I would really appreciate it, because I would really want to understand how conic sections work. I don't know if they teach this in pre-calculus, this specific thing, but I'm hoping they do. That's all. Thanks for watching.